Have you ever really stopped to think about the internet? Not the websites or the videos, but the actual journey your data takes. We're about to dive into one of the most incredible and seemingly impossible technical challenges ever solved: how the internet actually maps itself.
I mean, really think about it. You click send on an email, and in what feels like an instant, it shows up on a screen thousands of miles away. It's not magic, but it might as well be. How on earth does that little packet of data know exactly which path to take through a chaotic maze of billions of connections? Well, the secret is hiding inside these little boxes we all have called routers. You can think of them as the air traffic controllers of the internet. And each one has its own special map, called a routing table. This thing is like a superpowered GPS, telling every piece of data the absolute best turn to take at any given moment.
Now, here's where it gets kind of nuts. The internet is constantly changing. I mean, connections go down, new ones pop up, traffic jams happen all the time. Imagine if a person had to manually update the map for every single one of those routers every second of every day. It's impossible. The whole thing would just fall apart.
So, here's what we're going to cover. First, we'll dig into why that manual map is so impossible. Then, we'll look at how routers learn to talk to each other. We're going to explore a wild early concept called routing by rumor, see what happens when that gossip goes wrong, and then check out the super smart rules that were invented to fix it, leading us to the internet we know today. All right, let's kick things off by really getting a handle on the scale of this problem. Why wasn't a manual map just hard? Why was it literally impossible?
Okay, so when you boil it down, engineers had two basic options. On one hand, you have static routing. That's the manual way. Think of it like a paper roadmap. It's simple, sure, but the second a road closes, it's totally useless. For a tiny, unchanging network, maybe it's fine. But for the internet, no way. So, that brings us to the only real solution: dynamic routing. This is where the magic happens. The routers themselves become smart enough to build and update their own maps, on the fly. It's way more complex, yeah, but it's the breakthrough that lets the internet actually work.
So how do they do it? How does a bunch of disconnected boxes work together to map out a global network they can't even see? Well, first, they had to learn how to speak the same language. And they do that using something called a routing protocol. It's exactly what it sounds like: a shared language with a very strict set of rules. It's what lets one router tell its neighbor, hey, I know how to get to these places, and have that neighbor perfectly understand, trust, and use that information to update its own map. But, what happens when a router gets conflicting information? What if one neighbor says the best path is to the left, and another neighbor says it's to the right? That's where this really cool idea of trustworthiness comes in, and it's measured by something called administrative distance, or AD. It's basically just a trust score. The lower the number, the more the router believes the source. So a network that's directly plugged in has an AD of 0, that's gospel truth. But a piece of info it learned from a protocol like RIP has a score of 120. That means it's less trustworthy than a static route someone typed in by hand. It's a simple but brilliant hierarchy of trust. And this whole idea of trusting what your neighbors tell you brings us to the very first big strategy for dynamic routing. And honestly, it works a lot like human gossip. The official name for it is routing by rumor.
This quote right here just nails it. With this type of protocol, which is called a distance vector protocol, a router has zero clue what the whole network looks like. It only knows two things: the networks it's directly connected to and whatever its next-door neighbors tell it. And it just blindly trusts them. It takes their info, adds it to its own, and then passes that new combined story along to its other neighbors. It is literally a global game of telephone.
The classic example of this is the Routing Information Protocol, or RIP. Now, to decide the best path to anywhere, RIP uses the simplest possible measurement: hop count. A hop is just another router, so whichever path has fewer routers, that's the one RIP chooses, period. It doesn't care if one path is a super fast fiber optic line and the other is an ancient, slow connection. If the slow path has fewer routers, RIP thinks it's better. That's a pretty major blind spot, right? So here's how it all comes together in practice. About every 30 seconds, every single router on the network basically shouts its entire map out to all its neighbors. Those neighbors listen, combine that new info with what they already know, and figure out the new shortest paths. Then they update their own maps. This gossip spreads like wildfire until hopefully every router in the network agrees on what the map looks like. That moment of stability and agreement, that's a key term: convergence. That's the end goal. But here's the million-dollar question. What happens when the rumor being passed around is just plain wrong? This is where the whole simple gossip model can completely fall apart and create a total disaster.
So let's paint a picture. Imagine a network connection suddenly fails. The router that was plugged into it knows right away, of course, but its neighbor, it's still operating on old information because of that 30-second update timer. So for a short while, it still thinks that dead network is perfectly fine, and that tiny little window of bad information is all it takes to trigger a catastrophe.
And this is where we get a total nightmare scenario called a routing loop, or the more dramatic name, counting to infinity. Here's what goes down. Before the first router can tell everyone the bad news, its neighbor sends out its own regular update, which includes the old, wrong information. The first router hears this and thinks, whoa, awesome, my neighbor found a new way to get to that network. So it updates its map to point back at its neighbor. And just like that, you've created a black hole. Any data trying to get to that dead network is now trapped, bouncing back and forth between those two routers forever, burning up bandwidth and CPU until everything crashes.
Okay, so obviously a system that fragile couldn't last. So engineers came up with some really clever fixes, a set of rules designed to stop these gossip loops from ever getting out of control.
Let's break down these fixes, because they're pretty ingenious. First, a simple circuit breaker, maximum hop count. RIP just decides that if a path takes more than 15 hops, something is wrong, and it marks the destination as unreachable. That stops any loop from going on forever. Next up is split horizon. This is just common sense. You're not allowed to tell a router about a path that you learned from that same router. That one rule would have prevented the simple loop we just talked about. Then there's route poisoning. This is a much more active fix. When a link dies, the router immediately starts advertising that route with an infinite hop count, 16, basically shouting, hey everyone, this path is dead. And finally, you've got hold down timers. This tells a router that just chill out for a minute and ignore any new good news about a path that just went down. It gives the network time for the bad news to spread everywhere before trusting any new rumors.
So putting all those rules in place made early protocols like RIP actually usable. But the evolution didn't stop there. The protocols themselves had to get a whole lot smarter.
You can really see this just by looking at the evolution of RIP itself. The original, RIP version 1, was what we call classful. It was an old, rigid way of doing things that was really inefficient. Plus, it used broadcasts for its updates, which is like screaming out your entire address book in a crowded room. Super noisy. But look at RIP version 2. It became classless, which is essential for how the modern internet is built. It switched to using multicasts, so it was only talking to other routers who are actually listening. And it even added security with authentication, so routers could be sure they weren't taking directions from a bad actor. It was a huge step up.
So when you step back and look at the big picture, what we've seen is this incredible journey. It started with a simple, kind of flawed, but really clever idea, routing by rumor, and evolved into this sophisticated system with all these layers of rules to keep it safe. These protocols are the invisible nervous system of the internet, making millions of decisions every second. They really are the unsung heroes that make our digital world possible.
And that leaves us with one final thought to chew on. We've seen that a simple protocol like RIP only cares about one thing, the number of hops. But we all know that's not the full story, right? A connection's speed, its reliability, how congested it is, those things matter. So, if you were building a brand new routing protocol from scratch, what would you use to measure the best path? That's the exact question that engineers asked, and their answers created the super intelligent protocols that run the internet today.